Homework today. So how you guys doing? All right. Anybody else there? Hi, Adam. How's it going? Good to see you in the chess tournament finally. All right. Good afternoon, everyone. All right. So let's get started. Today, we are going to be solving a few problems on Ohm's law, looking at the whole idea of current, which we did last time, and then getting on to one last topic, and that is electrical power. Okay, and then we'll be all done. So let's do the homework first. I think it was, if I remember, let me look it up. It was 17. What in the world is that? Okay, cool. You're watching from India. All right, so you got, it was 17C, numbers 1 and 4. I think that's what it was. And then it was 17D, 2, 4, and 5. I think that's it. All right, so let's go ahead and jump into it. So 17C, that's got to do with current. And that's on page, let me see if I can go find it, page 969 of your books, and number 1. All right. So this is kind of, today we're going to be doing the last new lesson. All right, we're going to do a little bit of review, so we'll go over the answers and then do a little bit of review on Monday. And we're shooting for a test on Wednesday. If you guys want to learn more, we can do some more and then shoot for the test on Friday. But I see no reason to necessarily push everything in to the last minute. So I'd like to try to finish early and just do a test on Wednesday if possible, as long as you guys don't object. So I don't know. If you guys are okay with that, we'll just shoot for a test on Wednesday. All right, so here we go. We have current in a wire of a CD player. I think you guys still know what CD players are, although your kids won't. The current in a wire of a CD player is 5 milliamps. So current is, if you recall, I is 5 milliamps. So that's 10 to the third amps. And it says, how long would it take? So we're solving for time. How long would it take for 2 coulombs of charge? And that's going to be our charge. Charge is 2 coulombs to pass through a cross-sectional area of this wire. Okay, so basically just wants to know how long does it take for that amount of charge to go through. All right, so 5 milliamps, that's not a lot, but that's kind of normal for an electronic device. They don't typically use a whole lot of electricity, right? Especially if they don't have, if they're not big speakers or anything like that, right? And so we have the equation is I is Q over T. So the current or flow of electricity is the charge that goes per time. And so right now we can go ahead and plug things in, or I'm going to go ahead and flip this around first. So you can just, right now, anytime you have it set up like this, you can just flip I and T, or you can do it 2 steps, multiply both sides by T. So I, T equals Q. And solving for T, divide both sides by I gives you T equals Q over I. So our time that it's going to take is going to be the charge of 2 coulombs divided by 5 milliamps. Now this is where these prefixes really, you need to be careful about. So if you were just to do 2 divided by 5, you'd get the answer wrong, right? This is going to be 5 milliamps. So this is 5 times 10 to the minus 3 amps, which is going to make the time significantly longer, which we'd expect, right? 2 coulombs is a significant charge, whereas 5 milliamps, that's not a very large current. So it's going to take some time for this to occur, right? So that's going to be 2 divided by 5e negative 3. As long as we use the e functionality, we don't need to worry about parentheses. If you do the times 10 to the, you're going to need to worry about parentheses. So 2 divided by 5e negative 3 gives us 400. And what should the units be? 400. If our coulombs is just a measure of charge and amps, well, what is an amp? 1 amp is 1 coulomb per second. So if this is 1 coulomb per second, coulombs over coulombs cancel out, and you're left with seconds as our units. All right, so 400 seconds, you can just leave it at seconds. I don't think the question asks us for minutes. If you want it in minutes, you can go ahead and just divide that by 60. That's going to be like 6.66, and you can even subtract 6 from that, right? And then, and then just times 60, and that'll get you, oh, there we go. So we have 6 minutes, 40 seconds. Okay, so that's good, but you can just write down 400 seconds. That's sufficient. All right, so that's number 1. Number 4 is got to do with a compressor on an air conditioner draws 40 amps. So 40 amps, that's going to be our current. When it starts up. So when it starts, it's going to use significantly more electricity than when it's normally running. If the startup time is 5 seconds, so we have a time, not 5 seconds, sorry, 0.5 seconds. How much charge passes a cross-sectional area of the circuit in this time? So we're solving for how much charge, which is Q. Reconnect, please. There we go. All right, looks like we're back. A connectivity issue, gotta love it. All right, so Q. So same equation. Here we have the current equals the charge divided by the time, and here we're solving for your Q. And so we can just multiply both sides by T, so Q equals IT, which is going to be 40 amps times 0.5 seconds, and we don't even need a calculator for this one, right? So 40, yeah. So 40 times 0.5 is the same as 40 divided by 2. That's going to give us 20, right? And 20 amp seconds. Well, an amp, remember, amps are coulombs per second. So coulombs per second times seconds are, of course, going to be coulombs. So 20 coulombs. Nice. All right. So there we go. That is 17C. Any questions on that? Looks like we're good. Looks like we're good here in Connecticut. Looks like we're good in India. I think we're all good all around. All right. Let's jump down to 17D. And I think for 17D, what do? We did 2, 4, and 5. 2, 4, and 5. All right, and this is probably, I'm going to go ahead and just say 17D is probably going to be like the most important of all of these. Involves Ohm's law, V equals IR. And I don't know, I mean, it's a fairly simple equation, but it's fairly important in terms of electronics. So let's go ahead and turn the page over. Which is page 976. And number two. All right, back to our musical equipment here. Here we have a stereo with a resistance. Okay. A stereo with a resistance. So we have resistance. This is number 2 here. Is 65 ohms, is connected across a potential difference of 120 volts. And like I said before, 120 volts, that's standard here in America. 120 volts, if you plug into any of those, it's going to be 120 volts. Although you do have those bigger plugs. Have you guys ever seen those bigger plugs that you'll find, let's say, for your dryer or your refrigerator, they might have bigger plugs they're plugged into or something like that. But maybe the refrigerator might be normal, I think. The dryer is definitely going to be a bigger one. And yeah, I'm not sure. So occasionally you'll see those bigger ones. Oh, the stove. Yeah, your stove is also going to be one of those bigger plugs. They might be 240 volts or even more. Sometimes maybe even 300 or 400 volts on those things. But anyway, your standard is you're going to be using 120 volts. So there we go. What is the current in this device? So we're solving for I. Okay, so for solving for I, so V equals IR, which means we can just divide both sides. So let me write it here again. V equals IR. So if we're solving for I, we're going to divide both sides of the equation by R. That's going to get us I equals V over R. And if we look at this equation this way, it kind of makes sense, right? As you increase the voltage, you're going to get more current to flow. If you increase that electrical pressure or electrical potential, you're going to get more current to flow. However, if you increase the resistance to that flow, you're going to decrease the amount of electrical flow that you can have. So this equation really kind of makes sense when you think about the different aspects of it and what each component here means. The V is the causing your electricity to flow, the R is the resistance to that flow, and the I is the amount of flow. So here we go. Voltage of 120 volts, resistance of 65 ohms, which gets us 120 divided by 65, or 1.85, and our units are going to be amps. Okay, 1.85 amps. All right, next up, number 4. We have a current in a microwave, which is 6.25 amps. 6.25 amps. And the resistance in the oven's circuitry is 17.6 ohms. I'm assuming these are reasonable numbers. I don't know about most microwaves. What's the potential difference across the oven? All right, so we're solving for V. And that's going to be a simple V equals IR. No need to rearrange anything, just multiplying them together. 6.25 amps times 17.6 ohms. Let's do that. 6.25 times 17.6. It's nice that, okay, 110 volts. It's nice that when we're doing this, we're kind of ending the year on an easy note. At least I think that we are, right? So I think we're kind of ending the year on the easy note. So it was a little bit tougher earlier, this unit, but now I think pretty straightforward, right? We're not worrying about negatives or anything like that, and directionality and all that kind of stuff. So let me see, let's check the power. So we're going to calculate power here, and let me just give you we're going to kind of look ahead real quick just for fun and see what is the power of this microwave oven. Your power is going to be your voltage times the current, or I think it's typically written IV, so the current times the voltage. And so in this case, we have a current of 6.25 amps, and we have a voltage of 110 volts. 110 volts makes a lot of sense, but let's multiply this by 6.25. That's a really, really powerful microwave. Wait, what are microwaves normally? Maybe that's not really powerful. I don't even remember. How powerful is your microwave? So this is 688 watts. I thought microwaves weren't that powerful, but maybe they are. I don't remember. Just take a look at your microwave and see if it says the wattage of it. Maybe they are. Maybe they're like 1,000 watts sometimes. I'm gonna have to look at that. I'm sorry, I'm just getting distracted. I'm distracting myself. Anyway, that's not the answer. This is just for fun here. The answer was 110 volts. All right. So, I'm gonna go look and see how powerful my microwave oven is here right after class. I'm gonna check it out. But before we do that, that's chemistry there. All right, before we do that, let's do number 5, right? Let's see. Yep, number 5. Okay. There we go. Number 5 says, we have a typical colored television. It draws 2.5 amps, and I'm thinking that colored television is not your current colored televisions, but more like one of those old-timey ones. Because I think this book was written back in the day when, you had bigger TVs, but I don't know. So your typical colored television draws 2.5 amps of current. 2.5 amps. When it's connected across a potential difference, so you have the voltage of, what did it say, 115 volts. And what is the effective resistance? So we want to solve for resistance. So we have V equals IR. And if we want to solve for resistance, all we do is divide both sides by I. So your resistance is your voltage over your current. All right? So resistance is going to be 115 volts divided by 2.5 amps. 115 divided by 2.5, and that's going to get us 46. Your resistance is going to be in ohms, and that's it. All right. Any questions, guys? That's all of your homework. Did I lose you guys? All right, I still have 5 people, a whopping 5 people. Okay. All right. So, are we all there? Okay. Anyway, so whether we're there or not, let's go ahead and continue because I don't hear from anybody. I'm hoping you're there. I hope we have a good connection. So yes. Okay. Yeah, there are a few people here. Yes, Hannah and Adam are still with us. All right, so let's continue on. So our very, very last thing that we're going to be doing is going to be fairly straightforward, just one simple equation, and then we're done. In fact, I already showed you guys the simple equation, and that is electrical power. All right, well, let's go back before we jump into the equation is this. Remember what power means to begin with, right? So power, we defined it before as work over time, or you could think of power as some sort of any kind of energy over time. And typically we thought of power as a change in potential energy over time. Okay? Now we can look at potential energy in general for your electrical things, and a change in potential energy is going to be equal to Q times a change in your voltage. All right, so potential energy is equal to Q, the charge, times the change in. We can go ahead and say, we know that Q over T, is charge over time, is current. So this equals your current times your potential difference. Or we're going to simply write it as your current times the voltage. And so there's your equation for electrical power. Power is current times voltage. And so we can go ahead and try a sample problem you guys are going to have for homework. Let me go ahead and write your homework down up here. It's going to be 17E 1, 3, 4, and 5. So just skip number 2. I think it was somehow repetitive. So that's your homework due Monday. Your last homework that I'm going to give you guys, I will give you guys a review, but that's the last book work that I'm going to give you guys like ever. And let's go ahead and do the sample problem. We have a sample problem for 17E on, let's see if I can find it, page. And it's useful if you're watching this on a device other than your iPad, then you can just use your iPad as just as your book, essentially. Okay, so on page 988, all right? And so your sample problem is this. You have an electrical space heater, okay? So we got a heater. And heaters, they take up a lot of power. They use a lot of power. It's connected across a 120 volt outlet. So voltage is 120. And the heater dissipates, the power of the heater is 1,320 watts. That's a huge amount of power, right? But keep in mind, if you're using electricity to heat your house, your electrical bills are going to be through the roof. So it's probably a bad idea, especially in Connecticut, but I'm not sure about other parts of the world. Maybe if you're living in Florida, it's fine in the wintertime to use, electricity as heat, and then you would just use a heat pump or something like that. But you can't use a heat pump in Connecticut because it's too cold. So you have to directly convert electricity to heat, and you're going to use something like this. That is going to be ridiculous in terms of the amount of electrical usage that you would have. It would cost a lot of money. But anyway, so you have a heater that has this much power, 1,320 watts of power. And let's go ahead and calculate the resistance of the heater. So we want to know, what's the resistance? All right. Well, in order to use the equations that we've got, and you guys can go ahead and look at different equations, we don't see resistance anywhere in this equation, right? So we have P equals IV. We don't have I, and we don't have R. So we got a bit of a problem here. So what we can do is we can use our equation P equals IV, and we can also use the equation of V equals IR. So let me see. I think probably the best way to do this, if we want to solve for R, I think the best way to do this is to solve for I in this. And so let's go ahead and do that. You can actually solve for I, but I'm not going to. Instead, I'm going to substitute. So I is V over R, right? Divide both sides by R. And so then if power equals IV, then power equals V over R times V, okay? So power equals IV, this is I equals V over R, and then times V. So power, another equation for power, is going to be V squared over R. There we go. Now we have something that's solvable, right? We know the voltage, we know the power, we want to solve for the resistance, and what we can do is multiply both sides by R, divide both sides by P, and that's going to get us the equation of R equals V squared over P. Plug in some numbers. So 120 volts squared divided by 1,320 watts. And let's do it. Sorry, running out of room, and I'm going to save some paper. 120 squared divided by 1,320, and that's going to get us 10.9. What are the units? 10.9. Well, if its resistance is going to be in ohms, and that's it. So 10.9 ohms. Okay, so you guys, as you're solving these, you guys are probably going to be using this equation for power, but you might also use this derived equation for power, or power is your voltage squared divided by R. So either one of those are going to be useful for your homework. So we are done. We are all done, and I'm just wondering, will all the problems be like this? I don't know. I think all the problems will be similar, but you might be solving for voltage or for power or for current, so you can solve for all different kinds of things. But they're going to use, all the problems will use this equation or some derived equation like this, and that's it. So, like I said, I think this should be an easy end to the year. Not as bad as some of those things we were doing earlier, like with electrical field and all that mess, when we were worrying about your signs and all that kind of stuff. So this should be a little bit better, I think. I hope. And we'll do a review on Monday. Test on Wednesday. Cool. Is that all right? Do you guys want to do like new stuff and talk about circuitry on Monday, or are we good for the year? Because I feel like we're good. What do you guys think? Just test on Wednesday and get it over with? All, I don't know, 3 or 4 of you. Oh, look at this. This is classic. Adam is not only watching physics, but he's also playing chess. I know that Adam tests on Wednesday. All right, cool. I know that Adam just moved. We're just going to do a review on Monday. Right, yes, only review on Monday. So, all right, I'm going to close here. I'm going to check out the power of my microwave, and then I'm going to play chess, and yeah, we'll see how Adam does. Yes, ain't nothing like watching class and playing chess at the same time, especially when you're playing your teacher. All right, see you guys. Have a great weekend.